So we are recording the session. If anybody feels uncomfortable over that, let me know. Hey, how are you? I'm good, thank you. Alright, so I am Nishad, and you may call me as such. No need to add unnecessary qualifiers if you feel comfortable. Right, so I'll be discussing some graphs here over the next 2 days, today and tomorrow. And I talked to Amit Kumar, most of you know Amit. Yeah. So Amit has been teaching IIT for a while, and I also taught last year. So I'm trying my best to choose things that are in the difference of what you already taught. So hopefully it won't be repetition for most of you. If you find it repetitive, let me know. If you've already seen some of this stuff. So I'll start with the four-color conjecture, which is also a theorem. Since I will give a historical perspective, I will keep using the words conjecture and theorem interchangeably for the four-color conjecture, right? Because for a long time in history, it was a conjecture. So, right. So, does everybody know what the four-color theorem says? Does everybody know the statement? Yeah. Can anybody tell me what the statement is, or what is one equivalent version of the statement? Maybe a raise of hands. Yeah.
In the planar graph,
Yeah.
If we connect the vertices such that the adjacent vertices are not can't have the same color, then that graph can be colored in at most 4 colors.
Okay. And when you say you are coloring the graph, you are coloring what in the graph? You are coloring the vertices.
Yeah.
Because it's a
Looking at the vertices.
Sure. Right. So what you are saying, and can you tell me your name also?
Aitha Sharma.
Aritra. Okay, I'll try to remember, but please help me or repeat if required. Okay. So what Aritra is saying is that every planar graph is 4 vertex colorable. Vertex is an abbreviation for vertex. Right? And what this means is that you can color the vertices using 4 colors, so that any 2 adjacent vertices get distinct colors, at most 4 colors. If you don't use all 4, that's fine. If you use just 3, that's okay. Okay? So let's look at an example. So what's a planar graph? Can somebody summarize what a planar graph is? Maybe a show of hands. Okay. Right. If a graph can be drawn in the plane, so here is an example of a graph that has been drawn in the plane. I mean, this is the best simulation of the plane we have here, right? And what you see here is 2 edges are crossing at a point that is not an end of any of those edges. By end of an edge, I mean the 2 vertices that are the ends of an edge. Right? So this point here in the plane is not a vertex of this graph in particular. Right? So of course 2 edges can meet at a common vertex. Well, there's no way to avoid that, right? But they shouldn't meet at any other point. So this drawing here is not a planar drawing. Also known as embedding, but I'll try to use the word drawing. Yeah? This is not a planar drawing of this graph. This graph is A4, a complete graph on 4 vertices. Yeah? However, is this graph planar?
Yes.
Is this graph planar?
Yes.
It is, right? Okay, and how do you do that? Yeah, go ahead.
Sir, you draw a triangle.
Okay.
First,
Okay, you want me to draw a triangle?
and then take a point in between, and then connect the 3 vertices. Yes, sir.
Yeah.
That is K4.
Thank you. And you are?
Arches.
Arches. And you are? Yeah. Thank you. Good. So, thank you. So, this is the same graph drawn differently. And now you can see that in this drawing, there are no two edges crossing at a point where they shouldn't cross. So this is a planar drawing of K4, and the definition of a planar graph is that it is a graph that has a planar graph, that admits a planar graph. So therefore K4 is planar. K4 is planar. And how many colors would you need to color the vertices of K4? 4. 4? Yeah, everybody agrees. We can't do it less than 4. Yeah, okay. So 4 colors suffice for this small graph. The conjecture or the theorem says that they suffice for any planar graph. Right? So, right? Good. But what I want to talk about is an equivalent version of the 4-color conjecture. So the conjecture was proposed in 1853 by Q3. So conjecture 1853 by Q3, and it was finally proved 124 years later in 1976-77 by Apple and Hacking. And this was a pretty controversial proof because it was one of the first times that we had a computer-assisted proof in mathematics. And not only was the problem that it was computer-assisted, there were actually people who tried to verify the correctness of the proof, whatever was supposed to be human verified, and they ran into difficulties. And they communicated that with Hacken, and they kept fixing things. Eventually, most people agreed that the proof was correct. Finally, the more accepted proof came around in 1996-97 by Robertson, Sanders, Seymour, and Thomas. They got a Fulkerson prize for this, not that it matters. So they simplified the original proof of Apple and Hacken. The original proof had 1800 cases, roughly, and the final proof had 600 cases. It was still computer assisted, so people were still not happy. I definitely am not happy about it. For example, I cannot teach this. I cannot teach this not only here, but not even in a full course would I be able to teach this. So if I cannot verify it, then I'm not happy. I'm not verified it. I say it is a theorem because everybody around me says it. So anyway, so that's why I'm not very happy because I have not verified it myself. Whereas everything I will present today, I have verified it myself. So that makes sense. That's just okay. So that's the statement. And what I want to tell you about is an equivalent version by Tait. So there were multiple attempts to prove the 4-color theorem, of course, in these 124 years. 2 attempts really stand out. One attempt was by Tait in 1880. Tait attempted in 1880. Tait basically said, I have proved the 4-color conjecture. And 11 years later, in 1891, Peterson found a mistake in the proof of Tait. So, Tait gave a false proof of the 4-color conjecture. But in doing so, Tait made a very exciting, correct contribution, which was to give an equivalent formulation of the 4-color conjecture. And that formulation I want to tell you about. Instead of vertex colorings, it is in terms of edge colorings. Okay, and in fact, the original version of the 4-color conjecture is not even in terms of vertex colorings. It is actually in terms of what we call face colorings, right? But from face to vertex, the equivalence is actually quite easy. You just use a concept called plane duality. But going from either of those two edges is really non-trivial. So Tait said that you can color a planar graph. Actually, the equivalence was in terms of the face coloring version. So you can color the faces of a planar graph with 4 colors if and only if you can color the edges with 3 colors. And the coloring of the edges, what do you expect? When should 2 edges get different colors? When should they necessarily get different colors? If they have a common vertex, right? So if 2 edges share a vertex, in other words they are adjacent, then you would expect them to get different colors. So this could be one color, this could be another color, and this could be my third color. So you can see that we have colored this graph using 3 colors, the edges of this graph using 3 colors. And this is actually the version. Observe that this is not just any planar graph, it has the property that every vertex is degree 3. This is actually important. Every 3 regular, let me put some space here. Every planar, you expect planar to be there because the original statement is about planar graph, so somewhere planarity might show up. Every planar 3 regular graph is 3 edge colorable. Okay. So we have to use 3 colors to color the edges, so that whenever 2 edges are adjacent, they receive different colors. Yeah, is the statement here? Yeah. There is a mistake here. We need one more condition, which is 2 connected. Does everybody know what 2 connected is? Everybody knows what a connected graph is? Okay, can somebody tell me what a connected graph is? Maybe somebody who hasn't answered before. Can someone tell me what a connected graph is? Yeah. Between any two vertices, there is a path. In your sorry? Shrink. Thank you. Right. So between any two vertices, there is a path. That's when we say that the graph is connected. Okay. So any guesses about 2 connected? What would you think 2 connected might be? There are 2 paths. There are 2 paths. That is almost correct. If you want to state it that way, you need a condition on the paths. The path should be disjoint. We will call them disjoint paths. Although, of course, the 2 paths are not disjoint because they are both using the same 2 vertices. So, technically speaking, we call them internally disjoint. They should not have anything common except for the 2 ends because the 2 ends are the same. So, that's one way to define 2 connected. There exist 2 internally disjoint UV paths for all pairs of vertices U and V, where U and V are of course distinct. And this is the same as internally disjoint here, just means that if my 2 paths are P1 and P2, then the only common vertices are U and V. Yeah? Those are the only common vertices. Let's do an example. If this is my U, this is my V. Let me label the other vertices. Let's say this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. Then someone give me one UV path. Yeah? 0, 3, 5. 0, 3, 5 is one UV path. And can someone give me one that is internally disjoint from this one? Okay. 0, 2, 5. 0, 2, 5. Yeah? And you are? Nishad. Thank you. So these are 2 paths between U and V, one going from 3, one going through 2. I want to point out an important caveat here. The path given by Shreya was 0, 3, 5. that doesn't necessarily mean that you will be able to find another path that is internally disjoint with the path you already gave me. Can somebody give me a path so that there is no internally disjoint path with that one for the same U and V? Somebody different maybe? Yeah? 0, 2, 1, 4, 3, 5. We use all the vertices. Therefore, there is no path that is internally disjoint with this one. Right? So this is a common rookie mistake. So I wanted to point out that yeah, you get the point. Alright? Yeah. So in this graph, you can actually find two internally disjoint paths between any two vertices. This is one way to define two connected. There is an equivalent way to define two connected. Can somebody guess what an equivalent way would be? I'm not expecting the proof of the equivalence. That is a DIY, do it yourself. Right. So can anybody guess of another statement which would be equivalent to this statement, or you might want to think that is equivalent? Yeah. What? That is correct. Yes, any two vertices belong to a common cycle. That is a correct statement. Well, these equivalences generally have small exceptions. You have to exclude graphs on 1 and 2 vertices. So let's not worry about graphs on 1 and 2 vertices. If you don't worry about them, then the two statements are equivalent. For any two vertices, there is a cycle continuum. In fact, here you don't even need any small exceptions. Any other equivalences? Any other guesses? So I don't want to use paths and I don't want to use cycles. I want to just use the concept of a connected graph. Okay. Right. So the graph is connected, and if you delete any vertex, the graph is still connected. Turns out this is also equal. So two connected can also be defined as connected, and the graph minus any vertex is also connected for all vertices. Here you need some exceptions. For example, K1. If you delete a vertex, you get the null graph, which as per most definitions is actually disconnected. Because a connected graph should have one component, the null graph has 0 components. Okay? So, yeah, you get into these nitty-gritties, but I'm going to ignore them for now. For 2 or more vertices, these are all equivalent. Okay? So 1 or 2 vertices you will be careful. And the fact that they are equivalent in the DIY, do it yourself. If you have seen Menger's theorem, then this is a consequence of Menger's theorem. This is the easiest case of Menger's theorem. Okay? If you haven't seen Menger's theorem, that's okay. This is a much easier statement than Menger's theorem. How many of you have seen Menger's theorem or heard about Menger's theorem? Anyone? Okay. Anybody else? No. Okay. So it basically gives an equivalence between two definitions of connectivity. And here I don't mean just two connected, there's also notions like three connected, which are just generalizations. So let's come back to the statement. This is not what Tait proved. Tait proved that this statement is equivalent to the 4-color conjecture, which was back then a conjecture. Yeah. So proving the 4-color conjecture is the same as proving that every planar, 2 connected, 3 regular means every vertex is degree 3, graph is 3 colored. This Tait gave a correct proof of this equivalence. But then Tait said the above statement is clearly true, and therefore the 4-color theorem is proved and clearly false. As shown by Peterson in 1891, the statement is not clearly true, it needs a proof. Okay? So most mistakes in mathematics generally happen because of this, right? Because you just say, yeah, sure, this is true, and sometimes it is not clearly true, and sometimes it is not even true. Okay? Are there any questions or concerns? Anything that is not clear, this is a good time to resolve anything that's not clear in terms of definitions or terminology. Okay? So we'll continue in this direction. So what does it mean this is the question I want to ask you. What does it mean for a three regular graph to be three edge colorable? I mean, we know what it means, but is there another way to think about it? Three regular graph, every vertex is degree 3. And you want to color the graph's edges using 3 colors, so that any two adjacent edges get distinct colors. Is there another way to think about it? Raise hands, please. Okay, one. Have a seat, please. Alright, let's wait for people to settle in. Okay, thank you. Yeah, so just for the sake of the folks who just walked in, I'll quickly summarize, but I won't spend as much time, of course. This is the statement we are at. Every planar to connected three regular graph is 3 edge color. Right? 3 regular means every vertex is degree 3. 2 connected means the graph is connected, and if you delete any vertex, the graph is still connected. Yeah? And the statement is equivalent to the 4 color conjecture, which I suppose you might know. And this equivalence was proved by Tait in 1880. Yeah? Okay. I'm not going to prove this equivalence. I believe Amit might have proved this equivalence for some of you last year. If we have time today or tomorrow, we might go into it, but that's not my main focus. So I just want you to focus on the second statement and forget the original statement of the 4 color conjecture. And what we are now discussing is, for a 3 regular graph to be 3 edge colorable, right? So every vertex is degree 3, and you're coloring the graph in 3 colors, let's say orange, yellow, and blue, so that any 2 adjacent edges get distinct colors. What does this really mean? Is there another way to think about it? Maybe a show of hands? Okay, go ahead. Yeah?
Okay. So if you consider the subgraph of a particular color,
Okay, yeah.
then the degree of all of those vertices have to be 1.
Exactly. Cool. Thank you very much. So, what can you remind me your name?
Arches.
Sorry?
Arches.
Arches. Thank you. What Arches is saying is, consider the subgraph that is formed by a particular color. So consider all the vertices being there, but only take edges of a particular color. Let's say yellow. Look at this subgraph. So let's draw this subgraph for this example. Right? So this subgraph, there's the yellow there. This subgraph is, the ends of the board are not great. Anyways, so this subgraph looks like this. Every vertex has degree 1. You all agree? In this subgraph, every vertex has degree 1. This is called a perfect matching. Right? So a perfect matching there are multiple ways to think about it. One way to think about it is as a set of edges of the graph. You just think of it as a set of edges such that if you look at any vertex in general in a graph, then you will see only one edge from this set incident at this vertex. That means M intersection partial of V, where partial of V is the set of edges incident at V. This quantity is equal to 1 for every vertex of the graph. Is that right? Yeah, is that equivalent to what you were saying? Okay. Another way to think of this is as a subgraph. Rather than thinking of it as a set of edges, you can think of it as a subgraph. And then the definition becomes even shorter. It is a spanning one regular subgraph. Spanning refers to the fact that I am considering all the vertices, I am not deleting any vertices. One regular means what three regular means for 3 equal to 1. Right? Every vertex is every 1. Right? In this subgraph. So here what I have drawn is a spanning one regular subgraph of the original graph. Okay? So that's what a perfect matching is. And this is what I actually do for a living. Perfect matching. So now let's go back to the statement. So a 3 regular graph being 3-edge colorable. A 3 regular graph being 3-edge colorable. Can you now phrase this in terms of perfect matchings? I want a statement that is equivalent. Graph is 3 regular graph is 3-edge colorable if and only if blah. Okay.
There are 3 edge disjoint perfect matches.
Right. I'll just say 3 disjoint perfect matchings, but I think of the perfect matching as a set of edges. Okay. So, and you mean by disjoint, you mean pairwise disjoint. Is that correct? Okay. And you are? Got it. Thank you. So, this is the same as being 3 connected graph with 3 edge colorable to have 3 pairwise disjoint perfect matchings. Oh, yeah. Perfect matching, I will abbreviate to PM. Is that okay? Yeah. You all agree? For a 3 regular graph to be 3-edge colorable, it's the same as saying it has 3 pairwise disjoint perfect matchings. Yeah. And therefore, matching theory was born in 1880. Yeah, because the statement is equivalent to the 4-color conjunction. Equivalence took some time from 1853 to 1880, and this equivalence is not trivial. Like I will not prove it today, assuming that some of you have already seen it in the past. If you are interested, you can check out my YouTube channel, and everything is proved there. Right? So, if I am skipping some things and you feel that you lost out, you have FOMO, just go and check out the channel. Questions, concerns at this point? Anything that is not clear? Are the statements clear? Okay, so let's write down this statement now. Instead of saying 3-edge colorable, I will replace this and simply say as 3 pairwise disjoint perfect matchings. Yeah. Okay. So people got interested in perfect matchings because of this equivalence. This is at least one reason why historically people got interested in studying perfect matchings. Okay. So let's try to pay attention to the things, the conditions here. So 3 regular is kind of clear, right? If a graph has 3 pairwise disjoint perfect matchings, then at the very least, every vertex must have degree at least 3. Is that clear? Every vertex should have degree at least 3. Of course, you can say, what if I remove 3 regular and just say every vertex has degree at least 3? I'm not going to go in that direction. But so we'll assume 3 regular is fine. Also, there is a nice way. The 3 disjoint perfect matchings, M1, M2, M3, they comprise a partition of the H set. This will not happen if any vertex is degree 4 or 1. Yeah? So, another way to think of this is M1, M2, M3, they are pairwise disjoint. And if you take the union, you will get the H set of the entire graph. In the case of a 3 regular graph. Right? So, good. So we're not fiddle with this fellow, we'll keep this one. Let's think about the other 2. What happens if you drop planarity? Is it true that every 2 connected 3 regular graph has 3 pairwise disjoint perfect matchings? Is the statement true without planarity? Because if it were true without planarity, that would be nice. That should actually imply, generally speaking, that the statement is easier to prove because I don't need to use planarity anymore. Right? How do you use planarity to prove such a statement? Well, don't use it because the statement is motion neutral. Well, it's not motion neutral. Anybody knows of a counter example? If you drop planar, any idea if you know of a counter example? Any guesses what a counter example might be? K33. Try it. Draw K33. Check it out. Right? So let's try to fish for counter examples. So try K33. Everybody knows K33. 3 vertices here, 3 vertices here, and put all the edges, 9 edges. Yeah? Draw that and check whether it is 3 edge curve. K33 is not a counter example. It is 3 edge curve. Yeah, that's right. Good. Peterson graph. Peterson graph. And you are? Sorry? Can you repeat? Can you spell it? AB? Yeah. Able price. Oh, okay, nice. Because it was not on my bingo card. Okay, good. Thank you, Able. So, that's a Peterson graph. A very famous graph, arguably the most famous graph out there. And the Peterson graph is actually two connected, 3 regular, but not 3 edge curve. And it is the smallest such graph in the world. Right? This is the smallest two connected, 3 regular graph that is not 3 edge curve. Of course, this cannot be satisfying if you don't prove it. Therefore, let's prove it. Yeah? Let's try to prove this. We will not prove smallest. Smallest is a DIY and it's a pretty non-trivial DIY. But we will prove the rest. We will prove that clearly it is 2 connected 3 regular. That doesn't need a proof, that is an observation. Let's prove that it is not 3 edge curve. Yeah? I want you all to think about why it is not 3 edge curve. And I'll give you a hint to get started. I want you to consider this set of edges. What do I mean by this set? I am looking at a cut of the graph. What is a cut? I have partitioned the vertices into 2 parts. X is the 5 vertices inside the yellow circle. X bar is the complement, of course. And I am looking at partial of X. These are the edges that have one end in X and the other end is an X bar. Right? This is basically a generalization of this notation. Yeah? So this is a cut. This is called a cut of the graph. You partition the vertex into 2 parts, X and X bar, and you look at all the edges going from X to X bar. Yeah? So what you have here is 5 edges that are going from X to X bar. They comprise a cut and they also comprise a perfect matching of the graph, by the way. So I want you to think about this set of edges and I want you to think about a perfect matching with respect to this set of edges. Like, given any perfect matching, if n is any perfect matching of the Peterson graph, what can you say about m intersection partial of x? And if you have figured it out, just raise your hand and don't kill the fun for others. Right? So I'll come and talk to you. Yeah? So I want you to think about this. Take any perfect matching of the Peterson graph and think about the intersection of that with partial of x. And you can discuss amongst yourself, of course. And I'll also write down a more general statement in the meantime. So that you can also start thinking of that. G is a graph. Partial of x is a cut. M is a perfect matching. What can you say about? So I'll come and talk to you. What can you say about that? At least one. So at least one is correct. It's one. Section partial x. What can you do? Sorry. Right, so what I want you all to focus on is just this. Right? So there may be many ways to prove that the graph is not CH4. I will not be able to process all those many ways right now. But I would like to get to a particular argument by focusing on this particular thing. By focusing on this point. So some of you have already said that it has to be at least one. Okay, that is clear. Fine. It is at least one. Because there is an odd number of vertices here, odd number here. So in a perfect matching, think of perfect matching in a slightly different way. Think of each vertex being matched to another vertex. So that's the reason we call it perfect matching. Right? So the word perfect matching is not coming from the definition that I stated. It's coming from the vertex viewpoint. Every vertex is matched to another vertex. Right? Exactly. So if you think about it from that point of view, it is clear that this has to be at least one because there's an odd number here, there's an odd number here. Right? So everybody here cannot be matched amongst themselves. So somebody has to go there. But can you make it stronger? Instead of saying at least one, can you say something stronger than that? Anyone else? Okay. Anyone else? Could it be 2 for example? Can M intersection X partial X be exactly equal to 2?
No.
No. Why not?
I basically looked at the case.
Yeah, the economic example statement why is 2 not possible? There's a large number of vertices here.
Like if I took a color here or here, like if R is here and here, then like we get another R. So it's like we have 3, and
There's
because
4
nothing is
possible.
3, 1, 1.
It's 4 possible.
No, 4 is not possible because it's like at least 1. Everything is at least 1. So 4 ones will not be possible.
Sure.
And like if 2 are adjacent, then I like basically chase this and got it's 3 ones.
Okay. Right. And you can also go to the more general setting. I have a graph. I have some cut. Right? Everybody is looking at cut. Partition the vertices into parts. Look at all edges going from left to right. And I am looking at some surface matching. What can you say about this one? I'll give you a hint here. Does it have anything to do with this quantity? Are these two somehow related? The number of edges I use in a perfect matching from the cut, does it have any relation to the number of vertices on one side of the cut? Observe that we are mostly dealing with, because there is a perfect matching, the number of vertices is even. Because I am assuming that graph is a perfect matching. Okay? So therefore, either both x and x bar are odd or both of them are even. Does this have anything to do with n intersection partial of x? Are these two related? Supposing I have an even number of vertices on the left side and therefore even on the right side. What can you say about a perfect matching with respect to this cut? Anybody else regarding this?
Okay, got it.
Think about parity. Right? Parity is the state of being odd or even. When you think about parity and see if we can make some progress here. Right, so the point is that if I have an odd number of vertices on both sides, then how many edges will I use in the cut in a perfect match? Anyone? Now we can open it up. Odd number. You all agree? If I have an odd number of vertices here, an odd number here, then in any perfect matching, I will use an odd number of edges from the cut. Right? Because if I use an even number of edges from the cut, then now I have an odd minus even number of vertices, that is an odd number. They need to match amongst themselves. But an odd number cannot match amongst themselves. Right? So therefore, if this is odd, then this is odd. And now, by the same argument, you can convince yourself that if this is even, this is even. In other words, these are congruent mod 2. Yeah? Everybody okay with this notation? Right? Either both are odd or both are even. Okay, so now let's go back to the Peterson graph. In the case of the Peterson graph, what we have is x, the x I have shown you is odd. Therefore, the intersection of any perfect matching with the cut has to be odd. Total number of edges here is 5. So therefore, it has to be 1, 3 or 5. Yeah. So these are the possibilities. 5 is clearly possible because in a perfect matching, because all 5 edges is actually a perfect matching of the graph. You can convince yourself that 1 is also possible, that's not too difficult. There's a very beautiful symmetry going on here. Let me fix this edge. I'm now not going to take any other edges from this cut. Okay? I'm going to take only this edge from the cut. Therefore, these 4 vertices have to match amongst themselves. There's only one way to do this. And the inside 4 have to match amongst themselves. That is also a path. The only way to do it is this. And if you rotate this perfect matching 5 times, you get the other 5 perfect matching of the Peterson graph. The Peterson graph actually has exactly 6 perfect matchings. And I have shown you all 6. One is partial x. This other 5 are this fellow rotated 5 times. Yeah? And you can convince yourself with not much difficulty that this is actually not even possible. Just try it. Take 3 edges from this set. Either the 3 are consecutive or they are not consecutive. And for both cases, draw and convince yourself that the graph has no perfect matching, containing only those 3 edges. Basically, if you take 3 from the cut, you have to take all 5. There's just no way around. Right? So if you convince yourself that this is not possible, just by doing these 2 cases, which is not too difficult, then it means that to 3 edge color, you have to use only 1 and 5. That's not possible, right? How will you get a sum total of 5 by using just 1 and 5 3 times? 1 plus 1 plus 1 is 3, that's not 5. And if you already use 5, then you can't do anything. So, because this is not possible, it implies that this graph is not 3-edge color. Yeah? Okay. Good. So we can't drop planarity. That is the moral of the story. We cannot drop planarity. Okay. We don't want to drop 3 regular anyways. We can't drop planarity. The only thing that remains is 2 connected. Okay. So is it true that every planar 3 regular graph is 3-edge colorable? In other words, it has 3 pairwise disjoint perfect matches. Turns out, you don't even need to worry about disjoint. Even asking for a perfect matching is too much in a 3 regular graph that is not perfect. So I claim that in general a 3 regular graph may not even have a perfect matching. Connected 3 regular graph. I don't need connected really, but I don't want to think about this connected graph, they're annoying. A connected 3 regular graph need not have a perfect matching. You need to connect them to even have a perfect matching. Like to guarantee the existence, you need to connect. So can we make an example? When you try making an example of a 3 regular graph that is connected, it will not be too connected and it should not have a perfect matching. And I'll give you a small hint. You are allowed to use multiple edges. I did not say this until now because I did not need it. In general, throughout this talk, I will allow 2 vertices being joined by more than one edge. Okay? But I will not allow this nonsensical thing called a loop. Right? Because a loop cannot belong to any perfect matching. And as I said, I am only interested in perfect matching in life. So therefore, this is not allowed. Right? This is allowed. So can you use this and make a small example, really small example of a 3 regular graph that does not have a perfect matching? Maybe I'll give you something to start. This might be. I'll give you something to start. Add edges to this. Add only edges to this, no vertices. Yeah, if you have done it, just draw it and I can check it out. If you have made an example using parallel edges means this. I will also use the word multiple edges. If you have made an example using this, try to now make an example without using this. Yeah? Try to make some minor modifications. Now you may need to introduce vertices. But first try this. Only by adding edges. See if you can make a 3 regular graph that does not have a perfect matching. And the graph should not become too connected. In fact, I will tell you the vertex whose deletion should give you a disconnected graph. The vertex V should actually give you a disconnected graph on deletion.
And because simple. By utilizing more vertices. Introduce more vertices and make a simple curve. Questions here? This is actually an example. This is all just an example.
Yeah. So it turns out there is a smaller example. I could have done something simpler. I could have just done this. Oh no, wait.
Sir,
This doesn't work.
Yeah, I don't need it.
Yeah, sir. Yeah, this doesn't work. I need the bigger one. Yeah. For a moment, I got confused. That is an example for something else. We'll come to that one later.
sir,
Yeah.
Yeah. So this is correct. And what is this?
this is the adequate two extra vertices joined
Now
to
this
the
is to
three.
connect, right?
No, if we delete.
This is
Oh,
to
okay, because I got it.
So if it is two connected, it will have perfect. This is it's interconnected.
Okay, anyone else?
So one minute.
If it is two connected, there is a problem. Alright, so maybe I'll reveal the answer for everybody because most of you, perhaps everybody has gotten this. You just add these edges. Yeah, this is a nice sweet graph. And observe that this has no perfect matching. The easiest way to see this is to look at this vertex. If you delete this vertex, you get three components, each with an odd number of vertices. Everybody wants a piece of this, but everybody cannot have a piece of this because it is a perfect matching. Yeah, works? Okay. And now the next goal is, so this has parallel edges. Turns out parallel edges is actually not crucial. You can get rid of them. To get rid of the parallel edges, but still maintain the fact that it is a three regular graph, you just need to introduce more vertices. Right? And there is a very nice way to introduce more vertices. Once you see the drawing, it kind of becomes clear how to introduce more vertices. Sorry? Yeah, that's it. That's what we do. Yeah.
Just make outside.
Yeah, so what we'll do is we'll just add, the simplest way to proceed is to just add these edges, vertices.
This one, sir.
We're done. Yeah. Now we have a simple, three regular, connected graph
Yeah.
that is not two connected and it does not have a perfect match.
We can
So, you can't drop two connected because then you may not even have a perfect matching, let alone three pairwise destroying perfect matches. So that's just sacrilege. So the question arises, right, so we can't drop any of these conditions to still guarantee 3 pairwise disjoint perfect matches. Right? With this condition that the union is the whole set of the graph. If you want all of these things, you need all of these conditions. Yeah? The statement is true because the 4-color conjecture is true. Well, I haven't verified it, you haven't, I guess, but we all believe it is true. Yeah? Okay. But now let's talk about just 2 connected 3 regular graphs. Notice that to construct a graph without a perfect matching, 3 regular, we had to drop 2 connected. We dropped 2 connected, then we were able to get such an example. What if you have 2 connected? Turns out, then you will get a perfect matching. So that is what Peterson actually proved in 1891. Every 2 connected 3 regular graph has a perfect matching. Yeah, 1891. In fact, something stronger is true. In a 2 connected 3 regular graph, you can actually find a perfect matching. There exists a perfect matching containing any edge of your choice. Every edge belongs to some perfect matching. That does not mean that there are 3 pairwise disjoint perfect matchings. The Peterson graph, every edge belongs to some perfect matching. That is clear from the 2 perfect matchings I've shown you, and once you rotate the other one, you see that every edge belongs to some perfect matching. Okay? So that is true. That was proved by Schoenberger in 1934. So, stronger result. In the 2 connected 3 regular graph, each edge lies in some perfect matching. Yeah? Much stronger. You can cover all the edges using just perfect matchings. You can write a bunch of perfect matchings. I cannot tell you how many, but there is some set of perfect matchings, M1, M2, M3, M4, Mk. Their union is the whole edge set of the graph. The only thing I cannot guarantee is this things like disjoint and all that. The statement doesn't say anything about that. Yeah? So, what I would like to convince you all of is these 2 statements. Right? I will try to show you proofs of both of these, and most likely I'll try to get you to prove them in particular. But we need some tools. So, when they proved these results in 1891 and 1934 respectively, we as a species did not have a good understanding of graphs that have a perfect matching versus graphs that do not have a perfect matching. Right? There was no theorem that said a graph has a perfect matching if and only if blah 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 blah. Right? There was no such result. So they had to really work with their bare hands and somehow prove that these statements are true. Bill Tutt, one of the most prominent graph theorists of the last ever lived so far, I guess. Bill Tutt, I think born in 1918, passed away in 2002, I think. As a teenager, had actually come upon Peterson's manuscript. By the way, one small point, I say Peterson is actually supposed to be Peterson because it's Danish. So apologies to Peterson, but I'm too used to Peterson. So, anyways, so Bill Tutt as a teenager had come upon Peterson's manuscript, which proved that every two connected to the regular graph has a perfect matching. And in 1947, at the age of 30, I think, Bill Tutt actually proved a result about all graphs having a perfect matching. A graph has a perfect matching if and only if blah. That's called Bill Tutt's perfect matching theorem, also known as Tutt's one-factor theorem, because historically perfect matchings were called one factor because of this definition. And using Tutt's theorem, this is an easy corollary, and this is also an easy corollary. Yeah? So that is what we will do for the rest of today, at the very least, if not more. Yeah? I will tell you what Tutt's theorem is, and then we will deduce both of these results one by one. Yeah.
Sir, so Hall's theorem came afterwards.
Hall's theorem is from 1920s, 30s, if I am not mistaken. Yeah. No, Hall's theorem came before Tutt's theorem. So bipartite graphs, they actually had a pretty good understanding.
But they are general.
Yeah. This is for all graphs. Yeah. In fact, I'm very glad you mentioned Hall's theorem, because we will actually move towards Tutt's theorem from Hall's theorem. Okay. Any other questions or concerns? Yeah. Yeah. Sorry. Hall's, yeah, that's 1920s, 30s. I don't remember the exact year. It was 20s and 30s. Yeah. Tutt's theorem is 1947. Yeah, and Hall's theorem is actually more confusing because there were equivalent results like Lecture-1 theorem and all, which were already proved by the Hungarians. So it's a bit hard to really tell when the actual result was proved. Right? We call it Hall's theorem, but apparently there are other people who had equivalent results before Hall. But yeah, popularly it is called Hall's theorem. Yeah. So this is what we will do next. Let me see how it is. Before we do that, let me make one more small remark, a really cute remark, I hope. So, two connected three regular graphs have three pairwise disjoint perfect matchings is equivalent to the four color conjecture. But you may ask more generally, how many colors do you need to color the edges of a graph? Yeah, just like how many colors do you need to color the vertices, how many colors do you need to color the edges? So, since we are talking about three regular graphs, it follows from Gupta, using Gupta theorem, 1964-66, independently proved. Using Gupta, this is 64, and this is 66. Their words imply independently that every three regular graph, for a three regular graph, G, its edge chromatic number, Tait prime. So this is the edge chromatic number. This is the minimum number of colors you need to color the edges, blah 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 blah. Chi is generally used for vertex chromatic number, therefore I am using Tait prime. The edge chromatic number is either 3 or 4. You can color the edges of a 3 regular graph either with 3 colors, which is the same as saying there are 3 pairwise disjoint perfect matchings, or otherwise it's 4 colors. So in the Peterson graph, you can definitely color the edges with 4 colors. Right? In fact, it's not difficult to prove that if the graph is not too connected, then you will definitely need 4 colors because every edge will not belong to a perfect matching. So if you put 2 connected here, then this is more interesting because if it is not too connected, the edge chromatic number will always be 4. Okay? So 2 connected 3 regular graphs, the edge chromatic number is 3 or 4, and the ones which are not 3 edge colorable, they are called snarks. Snarks, these are the 2 connected 3 regular graphs that are not 3 edge colorable. The Peterson graph is the smallest snark. So why are they called snark? This was named by Martin Gardner, who was very influential in popularizing mathematics, especially in North America. Martin Gardner named them snarks after the hunting of the snark written by Lewis Carroll, who also wrote the Alice in Wonderland. Right? So they are these elusive graphs that, for a lot of problems in graph theory, if you solve the problem for snarks, you have actually solved it for all graphs. This is why snarks actually receive a lot of attention. To give you an idea about that, in November 2025, my PhD student Santosh and I, we went to Germany, pattern 1, for a workshop on snarks. The whole workshop was just for snarks. Right? 2 connected 3 regular graphs that are not 3 edge colorable. Therefore, they are 4 edge colorable. Yeah. So those are called snarks. The Peterson graph, of course, is the smallest snark in the graph. Okay. But anyways, that's not what I want to go into. I want to go back to, we might actually, if we have enough time, we may actually prove this statement tomorrow. Definitely not today, not happening. There is some chance we prove it tomorrow, not using Visi-Gupta, but possibly using another result called Gibbs theorem, which has a very beautiful proof. So we'll see. But anyways, let me go back to my earlier train of thought, which is to tell you about Cutts perfect matching theorem. So the theorem is going to sound roughly like this. Graph G has a perfect matching if and only if blah. Yeah? So we will go to Hall's theorem. Yeah? How many of you are familiar, or let's say not familiar with Hall's theorem? It's okay to not be familiar, I just want to know so that I know where to pitch. Right? So how many of you have never seen the Hall's theorem, or you don't recall what it sounds like? No? Nobody? How many of you have seen Hall's theorem? Okay. Cool. Thank you. Alright, so most of you have seen Hall's theorem, it seems. Can somebody tell me what Hall's theorem is? I'll write down the thing I want actually. I don't want the whole generality. I want the following. So, Hall's theorem. So I will take a bipartite graph. This is my notation G, A, comma B, where A and B are the 2 color classes. I will refer to A as the white vertices, B as the black vertices. So this is my bipartite graph. To have a perfect matching in a bipartite graph, at the very least I need cardinality of A and B to be equal. Everybody agrees? So let me assume that cardinality of A is equal to cardinality of B, otherwise it's not interesting anyways. I want to say the following, then G has a perfect matching exactly like this, if and only if blah. So what's the blah here? Raise hands. More hands. Yeah? Every subset? Right. So for any subset of vertices, any vertices, or you are choosing vertices from from one part, from A, let's say. If I choose some subset of A, then what do you want the neighborhood to be? Greater than or equal to its cardinal, right? So, for any subset of A, if you look at the neighborhood, the set of vertices that are neighbors of these vertices, its cardinality should be at least as large as its own cardinality. Yeah? And observe that this is actually symmetric. I wrote it for A, you can replace A by B and they are equal. Let's just make a drawing. This now. For example, this graph, here is a three regular graph. The fact that it's three regular is not really important. This fellow doesn't have a perfect matching. You will agree? There is a set of vertices in the color class A whose sorry, yeah, it doesn't matter. It's there's a set of vertices in the color class A whose neighborhood is too small. Is that true? No? No, this has a perfect matching? Yeah? Okay, let's go another graph. Yeah? Maybe I'll add some edges like this now. One of these two graphs doesn't have a perfect matching. This is not three regular by the way. Yeah, which one? G1 versus G2. G2 doesn't have a perfect matching, right? So agree? In G2, for example, I can take this to be my set S, and its number of neighbors is too little. Right? It has three vertices, the number of neighbors is only two. And of course, if there is a set like this here, then here also there is a set like this. You all see this? Okay. So this is Hall's theorem. If I have a set of white vertices that have very few black neighbors, well, it's a bipartite graph, so of course the neighbors of white vertices are black. Right? If I have a set of white vertices with very few black neighbors, very few means smaller than its own cardinal, then there is an issue. Because now everybody here wants to match with those, but there is only so many of those. Okay? So, how do you generalize this to all graphs? One standard complaint I hear about Tait's theorem is that many people who have seen Tait's theorem, they are unable to relate it to Hall's theorem. It seems like two completely different things. One that works for bipartite graphs, one that works for all graphs. And the issue with that is because we tend to focus on this set. Right? We are saying that this set has very few neighbors. Right? So the focus is on this set. Yeah? S has very few neighbors. Let's change the focus. Yeah? When you are focusing on S, I want you to focus on N of S. Yeah? Let's change the focus to this set. If you delete N of S, what happens to the vertices in S? If I delete all these vertices from the graph, what happens to each vertex in S? It becomes a single vertex component. It is an isolated vertex. Yeah? Okay. In G minus N of S, each vertex in S is isolated, by which I mean that it is a component in its own right. Yeah. If I delete n of s, these two, then all of these fellows are single vertices. Let's make a drawing. Okay, I think we all know what a perfect match is. So let me do this now. By the way, is the phone still recording or is it going to die? Maybe it already died, I don't know. Still working? Yeah? Okay, thank you. So let's make a drawing. If I delete some, let's say, 2 vertices or k vertices, I'm getting more than k isolated vertices. So I have a set of k vertices. Now my k is equal to 4, why not? And when I delete these vertices, in G minus S, all of these okay. I have a graph G. I am not saying this is a biquadrate graph. This is no longer necessarily biquadrate. It is any graph. G is any graph. And if I delete these 4 vertices, I get more than 4 isolated vertices. Can such a graph, biquadrate or not, have a perfect function? Can such a graph have a perfect function? No, right? You all agree? If I delete 4 vertices or k vertices and I get more than k isolated vertices, then do you all agree that the graph doesn't have a perfect function? This has nothing to do with biquadrate. Yeah? What is so special about isolated vertices? Can we generalize this? So this is my question. Don't blurt out the answer, please. So just raise your hands. What is so special about isolated vertices? Of course, isolated in the graph G minus S. Can we generalize this observation? What observation? G has no perfect matching. And I'll give you a hint. You can use this example, which is not biquadrate, to generalize your observation. Yeah? So, okay, think about this. Anyone else? So go back to how we proved that this graph doesn't have a perfect matching. We looked at this vertex and we made some argument. Try to go through the entire argument again and then relate it to this and see if you can generalize. Here's an ugly graph. Pretty ugly. Yeah. So does this graph have a perfect match?
No.
Okay, resounding no. Alright. So somebody was not answered yet, maybe? Why does it not have a perfect match? Why does this fellow not have a perfect match? Yeah. Well, you already answered, but okay. It's been a while.
So now note that we have how many orthogonal? 5 orthogonal.
Yeah.
Yes,
And now
different
that each of the orthogonal must be tied to something outside. These are the orthogonals are
When you say connected to something, you mean with respect to something?
connected to something else, some other component outside.
By connected, you make it more precise. In
Number
the
of
graph, it's
connected.
connected. Are you referring to some perfect matching or something?
No, like after you treat S,
Okay, okay.
all of these are disconnected components.
Sure,
right?
sure, yes.
And there is no edge between each of any of them.
That's right, because they're components. Yeah.
So they all connect to S. But the count number of odd components is 5, which is clearly get to the model S.
Yeah.
And each of those odd components must have something which matches outside of the
That's
S.
right. Yeah. Right,
So
exactly.
it must match something in S, but that's not
Right. Yeah. So the point is that when I delete these three vertices in this graph, these are the components I get. Clearly, I drew the graph in a certain way. Some of these components have an odd number of vertices. Some of them, one of them in particular, has an even number of vertices. But observe that the number of vertices of components with odd number of vertices is more than 3. 1, 2, 3, 4, 5. But it's more than 3. So in a perfect matching, each of these odd components, because it is an odd number of vertices, it will want to match at least one of its vertices outside. Everybody cannot match inside the component because it's an odd number. So every component of G minus S with an odd number of vertices will want to use one vertex from S at least, right? So this fellow wants to use one from S, this fellow wants to use one from S, this one, and observe that what the things they are counting are actually distinct. If a component uses a vertex in a perfect matching, then that vertex cannot be used by anybody else by definition of perfect matching, right? So there are 5 odd components, all vying for these 3 vertices. That's just a problem. Yeah. So what's the conclusion? That if you delete any set of vertices from the graph G, for the graph to have a perfect matching, the number of odd components of G minus S should be less than or equal to the cardinality of S. Yep. Everybody agrees? This is actually the observation we use here. You delete this vertex, single vertex. You got 3 components with odd number of vertices. That's a problem, right? Because 3 is greater than 1. So this is the easy observation. Easy once you have seen it at least. Right, so let's write it down. G is any graph if G has a perfect matching. Then for every subset of the vertex set, when I delete this set, the number of components with an odd number of vertices in G minus S, that's my notation, the number of odd components of a graph, that quantity is less than equal to the cardinality of S. All agree? Yeah, and this is not happening in Hall's theorem. When you have a set like this, in particular the neighborhood n of S violates that condition. That is why I said you need to switch the attention to this fellow. If you switch the attention to the neighborhood, then you see that Tait's theorem and Hall's theorem are actually related. And of course, Hall's theorem is a consequence of Tait's theorem. It requires some amount of work, but it's not a lot of work. Because of course Tait's theorem doesn't care about the color classes. It's about all graphs. I did not tell you the theorem yet. Sorry. I jumped ahead. I have given you an if-then statement. Can you guess what the theorem is? That is Tait's theorem. It's not just if-then. We proved one implication. Tait's theorem is this statement. This is Tait's theorem. Yeah, so what we have done is we have proved the easy direction. This is easy. And this is difficult. Right? And this is 1947.
Sir, what is CO video?
Sorry?
Number of odd components.
Number of odd components.
Acha, okay, CR.
Yeah.
Not okay.
By order, I mean number of vertices. Yeah. So anyway, so that's Tait theorem, and this is what we will prove today. For the rest of today, this is the proof. Yeah. And if we prove this, or maybe I don't know the order, we might actually assume Tait theorem and prove these two results, and then we might go into the proof of Tait theorem. But this is not too difficult. In fact, in the lunch break, you can try it if you have not had enough of it and perfect. Okay, so let's break for lunch. Thank you.